Okay, so I'm going to get started. The only announcement I have right now is that quiz number 2 is in recitations this week. So everything up through last Friday's lecture is fair game. So electron counting, like midway down page 5 in the notes for this chapter, is fair game. But everything after that is not going to be on the quiz. Okay, questions about that? Yeah? Yeah, anything that I want you to calculate, I'll give you the equations for.
When do you see the cutoff was for the material on the quiz? Was it Friday?
Yeah, end of Friday's lecture, yeah. Yeah, and in general, that's going to be how it is for the quizzes. Everything up through the Friday before is fair game. So, okay. Oh, and for the exam regrades, yeah.
So is it covering anything after quiz 1 through
Yeah, and I guess like everything from technically the start of OChem 1 is sort of fair game because it could always show up in a synthesis, but the emphasis will always be on stuff that has not been tested or quizzed on yet, so everything from exam 1 onwards. So, Okay, and for the exam regrades, I'm still going through the stack just because there's a bunch of them because of that one question that I worded badly, so I'll let you guys know I'm aiming to get them to lecture on Wednesday, but we'll see how it goes. So, okay. So where we left off last week was we started looking at ways to count electrons on transition metals, and we went through a couple of examples. What we're going to look at now is, first of all, like some fundamental steps of how reactions might go, or parts of reactions might go on transition metals, and then we're going to get into a couple of actual like useful to organic synthesis kind of applications of these. Okay, so reaction steps on transition metals. These are actually surprisingly limited. There's only a handful of things we can actually do, and it turns out that all of the more complicated reactions that we cover are pretty much just combinations of these happening in different orders that do things to the organic molecules, which happen to bind to the transition metals at certain points and then get spat out as different organic molecules later on. Okay. So there's kind of 3 subgroups, but there's, I guess, like multiple parts in each group. So first one is basically just ligand association or dissociation or substitution. All right, so this is basically exactly what it sounds like. A ligand either sticks onto the metal or falls off of the metal for dissociation, or for substitution, one ligand comes off and a new one sticks on to replace it. So usually X-type only get replaced with other X-type. And L-type for L-type. Okay. So if we're looking at, say, platinum here with 4 different L-type ligands, say like 3 ammonia groups on it, if one of them comes off, this is actually kind of an example of what we showed like last lecture, where one of the ligands drops off and takes both of its lone pair electrons with it. But now we're actually going to name this process as dissociation. Okay, so if we're doing electron counting on here, this one turns out to have a full 18 electron count. Dissociation is going to drop it by 2, so now I've got 16 electrons on the metal. And then if we bring in a different ligand, say, looks like I've got ethylene here. And stick that on instead. Now we're back up to 18 electrons. So dissociation drops your electron count by 2. Association increases it by 2. And dissociation and association together, this whole thing overall would be a ligand substitution. So if it's like one of these steps immediately followed by the other, then it's a substitution. But you can frequently get just dissociation happening by itself or association happening by itself. Okay, so that one's reasonably simple. If you go through the electron counting thing, you can sort of, I guess, prove the counts to yourself. Any questions about that one? Okay. So the next one, or the next pair of them, is a little bit more complicated than this. And that is oxidative addition. And its opposite, reductive elimination. Okay, so here the basic idea is the metal inserts itself into a bond between two other atoms. So this is going to end up actually adding two X-type ligands. And so if you go through the electron counting, because you're inserting two X-type ligands, you're actually going to increase the oxidation number by 1 on the metal, or the oxidation state. Or by 2, I mean. Okay, so that's oxidative addition, because you're oxidizing metal. Reductive elimination is exactly the opposite of that. You take two X-type ligands that are on the metal, you kick them out with a bond together, and the metal drops its oxidation state by 2. Okay, so reductive elimination is basically oxidative addition backwards. Okay, so how this might look. So you've got two atoms here that are bonded together, maybe a couple of hydrogens, and the platinum here can insert itself into the bond between those two hydrogens. And hydrogens, if you remember, are both X-type ligands. So you're going to end up with an oxidation state that's 2 higher on the platinum here. So if you do electron counting, platinum here is 14 electrons and oxidation state of 0. And here it's 16 electrons and an oxidation state of +2. So it's getting more electrons towards its 18 electron limit, but the downside is it's increasing its oxidation state. Okay, so doing this in the forward direction is oxidative addition. Doing it in the backwards direction is reductive elimination. So reductive elimination would be you start with two X-type ligands on the platinum, they go off bonded together, and now the platinum has less of an oxidation state.
Question?
Yeah.
I'm confused why there's an oxidation happening and it's gaining electrons.
So think of it in terms of, I guess, when these hydrogens were bonded together, they both had sort of an oxidation state of 0. Now they're both bonded onto something that's less electronegative than themselves on average. So both of these are acting like X-type ligands. So if they got kicked out, they would be like H with a minus charge, both of them. And so it's sort of like they're each taking a negative charge, and so the platinum is at least officially taking a +2 oxidation charge. So we have actually seen something kind of similar to this before, although we never really got into the details, and it's not exactly on a transition metal. But if you guys remember Grignard formation, so here you've got a magnesium atom. You have a halogen attached to whatever carbon, let's just say CH3, and the magnesium ends up, it goes from neutral, so oxidation state of 0, to oxidation state of +2. Or in other words, if you split these up into ions, magnesium would now be a +2 ion floating around. So it's not exactly the same, but it's, because magnesium isn't really using the 18 electron limit, but it's kind of a similar process where the magnesium ends up bonding between two different atoms and taking on a 2 charge, I guess a charge 2 higher than it was before, if that makes sense. And the other two end up with negative charges if you kick them out on their own, which is how they act. That's why Grignards have the CH3 with a negative charge is another way of showing that. Okay, so questions about that one? Okay, cool. So one thing that is worth noting, I guess it doesn't matter at all for any of these ligands because they're fairly small and simple, but it will later on when we're looking at bigger molecules doing this, and that is that whatever is going on in the stereochemistry at the group that added on, like say we had an asymmetric carbon here, its stereochemistry would be retained. All right, so like an R carbon would stay R or vice versa. Okay. So I guess one other example of this that we sort of glimpsed before but never really got into is if you guys remember hydrogenation, where I did this sort of little fake cartoony mechanism of how that works, where you've got the surface of the metal and the hydrogen comes down and bonds onto two different sites on the metal. That's kind of what's going on there, where the hydrogen comes down as like two H's together, and then it splits up into two H's bonded onto the metal. Turns out there's, I think, more complicated stuff going on there, but that's kind of the general idea. Okay. So the third category that we're going to look at is, again, two processes that are the reverse of each other, and that is ligand insertion and beta elimination. This is the only one where changes actually occur like within the ligand group. So for ligand insertion, an L-type ligand inserts itself into the bond between a metal and an X-type ligand. Which is going to make a new X-type ligand. Okay, so that's for ligand insertion, and then beta elimination is the opposite. Okay, so how that looks is okay. So just as a reminder here, the pH stands for phenyl, which is an aromatic ring with a single bond coming off of it. Oh, this one's fixed, sorry. Oh, the top one? Yeah, sure. Okay. Okay. Sorry, any other questions?
What's the compound in the top left? Or, yeah, to the platinum in the top left.
Oh, pH3P. So this is one that we're going to be seeing a fair bit of, but it's one subset of like phosphorus with 3 R groups on it, which is kind of analogous to like a tertiary amine, but phosphorus is one down from nitrogen in the periodic table. So the phenyl group is just an aromatic ring with a bond coming off of it. So triphenylphosphine is how this is called. Let me draw it over here in the corner actually. So triphenylphosphine is going to be a phosphorus with three aromatic rings sticking off of it. This is kind of an L-type ligand that's kind of popular because it tends not to actually get like chemically involved in whatever's going on. It's just kind of filling space on the metal. Okay, so triphenylphosphine. But really you can just think of it as like generic L-type that doesn't do anything useful, particularly during the reaction for now. Okay. So what we're doing is a ligand insertion here. So we've got an L-type ligand. We've got a couple to pick from, but I guess triphenylphosphine is not going to do much. So what's actually going to be involved here is this ethylene L-type ligand. And the way that works is, out of the 2 atoms here, one of them ends up bonded to the platinum, and one of them ends up bonded to an X-type ligand that was previously on the platinum. Turns out it's going to be phenyl for this example, but it could be other things instead. So we're going to end up with these 2 ligands stuck together now. So basically what we're doing is making a new X-type ligand. This whole thing is now X-type because it's got a carbon directly bonded to the platinum, and if you kick this out it would have a negative charge on carbon. But it's sort of incorporating the old X-type ligand that was on the metal by itself, the phenyl group. Okay, so this forward direction is ligand insertion. Let me move this around a little bit. And if we did the same thing in reverse, if we took this ligand, spat out a group from what would be the beta carbon on here as a new X-type ligand onto the metal, and then had this thing become a new L-type, then we'd be going, this process in reverse would be beta elimination. Okay, so that's it. That's the entire set of moves that we have for transition metals. So some of them are kind of a little bit more visually obvious than others. Like the ligand insertion beta elimination is sort of the most complicated out of the set. But this is actually the one that lets us form new carbon-carbon bonds a lot of the time, because when we make this bond between the L type and the old X type, we're actually getting a new carbon to whatever the group is, phenyl in this case, bond out of it. We can also make carbon-carbon bonds through oxidative addition too, if you look at it, through reductive elimination, I should say, because if we had two X types here that were both carbons, if we spat them out from the metal, we'd have a new carbon-carbon bond forming between those. So those are two ways that we're going to see that end up generating new carbon-carbon bonds during the reactions where we're going to see them pop up. Okay, so questions about those? Yeah?
How do you know that adds, if you're doing the backwards and hadn't seen the front forwards, how do you know that it would become the double bond?
So I guess if you know that it's got to form a new X type and a new L type, and the X type is going to be sort of on the beta carbon 2 away, so we know that this becomes an X type, and then this part becomes an L type. And I guess the only example of L-type ligands that we've seen that are all carbons are where the pi bond is the one contributing, because there's not likely to have like an actual lone pair on the carbon with without a negative charge, which would make it X-type. So, welcome. Thanks. Yeah.
Can you only do the third one with some sort of carbon group, or like we would do it, this example with the next type?
For the bromine? Sorry. Yeah, you could do it with the bromine as well. We tend to focus on the new carbon-carbon bond-forming ones because that's kind of what gets us what we want usually. But yeah, it could totally have done it with the bromine instead, and that would still be a ligand insertion. So, Okay. All right, so this might sort of make more intuitive sense once we start actually seeing it in context and using it to do some actual chemistry. So let's get into that. Okay, so the first one we're going to look at here is the Heck reaction. Okay, so what this does is it's going to create a bond between an alkene to an aryl or a vinyl halide. Okay, so this right here, we spent a lot of this chapter looking at the chemistry that these things can't do. So finally, now that we're bringing in transition metals, here's finally some chemistry that we can do with aryl and vinyl halides, other than SNAR, which is pretty limited. Okay, so overall, here's how it might look. You got an aromatic ring, for example, with an X on there. And we're going to bring in an alkene. With an R group on it. Sorry, thanks. Thanks. Okay, so the other reagents that we're going to use here we can talk about, but these are going to be palladium with phosphorus. So PAR3 here is sort of like a more generic version of PH3 or PH3P. PH3P. So PAR3 is a triaryl phosphine. So it's a phosphorus with three kind of nondescript aromatic ring kind of groups on it. We're not being specific as to what. But it turns out when you bring in the palladium, you're going to have 4 of those ligands on it, so 4 L-type ligands. And then it turns out you also need sort of a mild base, often triethylamine works pretty well for this. Okay, so what's going to happen is you end up losing the halogen off of here, and you end up losing one of the hydrogens off the alkene, and you just form a bond right between them. So like this. The problem is, I didn't draw the other possible product in the notes, but there's not a whole lot of pickiness between which end of the alkene is going to react, so long as you can pull an H off of one of the vinyl carbons. So if you're doing it with a non-symmetrical alkene, you could just as easily get the wrong end of the alkene sticking onto the ring. Okay. All right, so questions about that first of all. Okay, so what's the byproduct going to be of this reaction, just based on the atoms I'm losing from my two starting materials? Yep, HX, which is why I need the ET3N. It's pretty much just there to soak up the HX byproduct. So another option that we've used in the past to do that sort of job would be pyridine. I think you could also use pyridine for this reaction too, but I'm not sure if it's going to interfere with a transition metal. So for some reason, triethylamine is kind of the traditional way of doing this. Okay, so questions about that before we get into the mechanism? Okay, so mechanisms for these things are going to look a bit different from how we're used to seeing organic mechanisms. Because the transition metal is actually a catalyst, it's not getting used up during the reaction. What we do is usually focus on the role of the transition metal. So rather than showing like starting material, intermediate product, we're actually going to draw a closed loop where we're focusing on the metal comes in this way, it does some stuff, it spits out the organic product in the meantime, and then eventually it gets back to where it was as a catalyst. So we're doing this totally centered on the transition metals point of view. But before we can start having the palladium do anything useful, so palladium with 4 L-type ligands on it, if you go through and count the electrons, palladium has 10 electrons, these each have 2, so right now we're at a full 18 electron count. Which means that we can't really add anything else on there because it's full. So before we actually do anything useful, we're going to have to drop some stuff on there to make space for the chemistry that actually needs to happen. Okay, so the very first thing, like sort of the pre-reaction, I guess, is where the palladium loses 2 of its triaryl phosphines. So it goes from 18 electrons down to 14 electrons. Okay. So that's how we're going to get things started. And now we're in sort of, I guess you could consider this like the pre-catalyst. This is the form you buy it in and you add it to the reaction. But the actual thing that's going to start the closed loop catalytic cycle is this more active 14 electron version. Okay. So for the closed loop part of this, I'm just going to abbreviate these as L. Just because they don't actually do anything in the reaction, they're just taking up space and filling the electron count on palladium. and they're kind of cluttering the thing up. So for the rest of the catalytic cycle, I'm sort of summarizing those a little bit. Okay, so the actual catalytic cycle. So we start out with the palladium has 2 L-type ligands on it. That's those 2 triaryl phosphines. And the first thing that's going to happen is the aryl halide that we're using, say, in the notes I stick with bromobenzene for my aryl halide. This is going to do an oxidative addition, which I'll abbreviate as oxad. So we know that oxidative addition, this bond between the 2 parts of the aryl halide splits up and they both become new X-type ligands. So now we're going to have palladium with a couple of ligands, and it doesn't really matter too much like what sides of the metal you show them on. I think in the notes I show them on opposite sides, but depending on the exact geometry, it kind of varies depending on the metal. So you can show that however. Okay. So we've got our phenyl ring and our bromine stuck to the palladium. Now what's going to happen is an L-type for L-type ligand substitution. So the alkene that we're using, I'll use a simpler alkene to keep things tidy. So like, say, just ethylene is going to swap out for one of the L-types. So like that. Okay, so we've got the 2 parts that we know need to get stuck together, the aromatic ring and the alkene. We've got them in the same place now. If we want to end up making a bond between them, which we know is going to happen from the overall reaction, this is where ligand insertion comes in, because we want this phenyl ring to end up bonded to the alkene molecule. So ligand insertion here is going to look like this. And now if you're looking, we're pretty close to having made the product that we're aiming to do. We just made our new carbon-carbon bond, and now I just need to figure out how to get this whole thing off of there in one piece. All right, so the easiest way to do that, as it turns out, is to do a beta elimination, but not on exactly the same groups that we did the ligand insertion in. So we're not exactly working backwards through here. We're doing a beta elimination that spits out something different than the phenyl group we had originally. All right, so beta elimination. We're actually going to spit out a beta hydrogen from this thing. So in other words, we're going to leave one of these on the metal, one of those H's. So we get an H here, and the new L-type ligand that we're making looks like this. It's lost one of its hydrogens, and now it just has an alkene where one of the alkenes is bonded to the aromatic ring that we started out with. Okay. Yeah, I think I've got enough space to write it. Okay. All right, so at this point, we've actually got our product all done. That's the thing we're aiming to make, the new bond between the aromatic ring and the alkene. So now we can just do another ligand substitution. And replace this whole thing, which, looking at this from an organic chemist's point of view, that's the whole reason we're doing this. But looking at this from the transition metals point of view, from an inorganic chemistry sort of view, the palladium is still doing its thing and has the cycle to complete. So we're actually going to replace the whole product molecule with another copy of L, which is our triaryl phosphine. And meanwhile, we'll still have H and Br on there. Okay, so then the last thing we need to do to close the loop, we can get back to where we started with palladium, is spit out H and Br. What kind of move is that going to be out of the steps that we covered over there? Not quite. So we're spitting out two things that are single bonded to the metal, but we want them to go off single bonded to each other. Yep, reductive elimination. And so we're losing HBr in this process, which is how we get the HX byproduct. Okay. All right, so it's a lot of steps. Like, all of them are fairly, I guess, not too complicated, but then when we put them together, we get something that's quite a bit more complicated, and we can actually accomplish something useful with it. So other questions about this one? Yeah?
How do you control whether or not the bromine or the phenyl group?
Yeah, good question. So a lot of the time, like, you will get some byproducts, but you can sort of tip it in the direction that you want. I think because forming the carbon-carbon bond ends up being sort of more favorable overall than forming the like carbon-bromine bond that you had to start out with. And a lot of that actually is emphasized because if you look at the products that we're making, we always have this conjugation between like the aromatic ring system and the double bonds here. And that's actually providing a fair bit of stability that you didn't have previously when it was just a halogen. So a lot of it is just like you sort of throw it onto the palladium and hope for the best, but it's sort of tilted in the right direction by the product stability that you're getting out. Okay. Okay, good. So I guess I did cover after this in the notes the fact that there's not much selectivity between which end of the alkene does this versus the other, so you can get two different products out of it if the alkene is not symmetric end to end. There is actually one other thing to worry about here. Actually, I can do it up here. So the downsides are there's two products possible if the alkene is asymmetric. And if the alkene is cyclic, it turns out it actually gives you a double bond in the product, one away from where you would expect. We won't get too much into the details on that, but it turns out to just be a limitation of the geometry going on at the carbon during the reductive elimination step. Yeah, I'll get it down here. Okay, so if you have an aryl halide here, plus this alkene, you would expect this where it's conjugated between the aryl halide and the alkene, turns out that doesn't actually form. What you get instead is this, unfortunately. Okay. So just kind of one added wrinkle that's annoying, that doesn't quite give you the product that you would otherwise expect. Okay. So questions about that? Okay, cool. So I guess if you've been looking at the exam archives, I'm not expecting you to regenerate like any of these catalytic cycle reactions from scratch entirely, but I might give you like half of them and ask you to fill in the blanks, or I might just give you like a description of what step happens and like which other ligands are involved, and then you have to show what happened afterwards. So you don't have to memorize the whole thing, but you should know enough about the fundamental steps that if I give you like half of it, you can sort of fill in the rest of the details as you go. Okay. So, all right, so that's the Heck reaction. It's kind of the original one in this category, but it's not as specific as it could be. Partly because we're sort of using an alkene as one of the groups, and there's multiple different things that could happen there. The next one we're going to look at is the Suzuki reaction. And this is a little bit more locked down as far as regiochemistry. Okay, so this one, we're going to see a fairly new functional group, at least one that we haven't really talked about much before. This is using boron with a couple of H's on it, and this molecule is called an aryl boronic acid. All right, and this specific one would be phenyl boronic acid, but whatever aromatic ring you want on here you can use instead. And then again, we're going to use an aryl halide. Okay, so here you're going to ultimately end up dropping the entire boron group and the halogen group and forming a bond between two different aryl rings, which is not something we've ever had any idea of how to do before. So this reaction is super handy for kind of circumstances that would otherwise be pretty difficult to deal with. So we're making a new aryl-aryl bond. The reagents that we use for this are, again, some kind of triaryl phosphine, or 4 of the triaryl phosphines on palladium, and then either NaOH, sodium hydroxide, or sodium bicarbonate. Okay, so there's actually a whole family of reactions that are kind of like this that use different groups instead of boron. There's like zinc-based or tin-based, but Suzuki is kind of probably the most popular out of them, so it's the only one we're going to cover. Okay, so I think I got 5 minutes left. This catalytic cycle is actually a little bit simpler than Heck was, so I think I can get through the whole thing. So the reaction starts pretty much the same way that Heck did. We have to drop 2 L-type ligands off the metal to get it ready first. So we're making palladium with 2 L-types coming off of it. And then That gets us to here. So the same starting point as in HEC. And actually the first couple steps are the same too, where we have, first of all, oxidative addition of our aryl halide Okay, so the palladium kind of wedges itself into that middle of that aryl halogen bond. And then ligand substitution. This is where things start to look a little bit different. Instead of using an alkene, we're actually going to use an X for X type ligand substitution. So rather than using an alkene for one of the L-type ligands, we're swapping in an OH minus for the halogen. Okay, so that looks kind of different, having an oxygen on there. Okay, so this is where the boron or boronic acid groups gets involved. I guess if you guys remember from the times we've seen boron in the past, boron actually has an unfilled octet. So while this stuff is going on, this particular step we're going to see doesn't actually involve the transition metal doing anything at all. It's actually between one of its ligands and a different molecule. So oxygen donates electrons to boron. So we've got an OH group here. And the oxygen has actually gone off and made a bond onto this boron with whatever R group's on there. So like that. Okay, so I think in the book they describe this step as something else, but if you look at it, we're all set up to do a beta elimination. So like this whole thing is an X-type ligand, but we want to get the R group onto the palladium. So we can just do pretty much a beta elimination, pop this R group off of here from the beta position right onto the palladium, and then have this whole thing go off together. So we're spitting out boron with 3 OH groups on it. Okay, so now it's starting to look kind of like the end game of this thing. We've got the phenyl group and whatever other aryl group was on the boron to begin with stuck to the palladium together. And now all we need to do is to get them together is spit them out during a reductive elimination. And get the catalyst back. Okay, so I'm going to wrap it up there for now. We can cover the last of these reactions on Wednesday.